Hello, this is Rick Nye. I am a Regional Sales Manager at Gefran. On behalf of our company, I want to thank you for tuning in. Today I will be doing a technology overview of magnetostrictive linear sensors and Hyperwave technology. Throughout the presentation, please use the chat window to ask questions. At the end of the presentation, there will be a question and answer session where I will answer these. If you prefer, you may email questions to richard.nye@gefran.com. That's richard.nye@gefran.com. First, let's talk about what a linear position transducer is. A position or linear displacement sensor is a device whose output signal represents the distance an object has traveled from a reference point. It can either be an absolute sensor or a relative one. In the diagram below, the two blue dots each have an absolute distance measurement from a point that is defined as absolute 0. They also have a relative measurement between them. The dots could either be stationary or moving. The same concept holds for an angular sensor, measuring the degrees of rotation of an object with respect to a fixed point or axis. In this diagram, you will see that absolute 0 is defined as true north. The red dot on the right has an absolute measurement of 120 degrees. The red dot on the left has an absolute measurement of 240 degrees. The relative measurement between them is 120 degrees. A linear displacement is a movement in one direction along a single axis. A displacement measurement also indicates the direction of motion. Usually this is indicated in millimeters or inches. A rotation is a circular movement of an object around a center or point of rotation. It can be in either direction. Angles of rotation are measured in degrees or radians. A position sensor converts or transduces the physical quantities such as millimeters, inches, degrees, or radians into an electrical signal such as amperes, volts, or digital output that is compatible with a data acquisition system. Examples of analog outputs are 0 to 10 volts DC, 4 to 20 milliamps, and many others. Examples of digital outputs are CAN Open, SSI, and Profibus. In a moment, we will dive deeper into magnetostrictive technology, but first, for comparison, I want to talk briefly about two other linear technologies, LVDT and potentiometric. First, we'll talk about LVDT. Many use the term LVDT universally to describe all linear sensors. This is not accurate. It is only one of the technologies used. Linear variable differential transformers, or LVDTs, operate on the principle of a transformer to measure displacement. The device consists of a primary fixed winding, blue in the drawing, that is powered by an AC power source, and two fixed secondary windings, red in the drawing. These primary and secondary windings are typically wound on a hollow form. In the middle of the hollow form is a movable core that is attached to the item to be measured. When the movable core is centered with the primary and secondary windings, as shown in this picture, the voltage induced in the secondary windings is of equal magnitude but 180 degrees out of phase, and thus cancel. This would indicate a linear measurement of 0. Moving the core left or right induces a greater voltage in one of the secondary windings than the other. The difference, or differential, in the voltages represents the linear measurement. This is why the device is referred to as linear variable differential transformer. Advantages of this technology. It is robust because the movable core does not touch the coils. Since it is based on an electromagnetic coupling, the resolution is infinite, or limited only by the data acquisition system. Disadvantages. Due to the core within a tube design, form factors of the sensor are limited. Being electromagnetically coupled, the device is sensitive to electromagnetic interference. Temperature affects performance. Because of the above disadvantages, LVDTs are used less commonly now than magnetostrictive and potentiometric sensors. A potentiometer is an electromechanical device that provides a voltage variation value by a ratiometric electrical signal proportional to the measured displacement using the absolute position of the shaft or cursor. The potentiometer main elements are the board with a resistive track and a collector track, shown in green and black in the picture, and the wiper with the different contact brushes that slide the length of the board and connect the tracks. The advantages of potentiometric technology are that they are inexpensive, they're immune to EM interference, they have great linearity, and infinite resolution. Disadvantages: they are not touchless, meaning they require the wiper to physically slide across the resistive and collector tracks. Although the life is long, it is not as long as a touchless technology like magnetostrictive. They are limited to a single cursor, and being a simple voltage divider, they are voltage output only. Gefran is also a leader in two other technologies, Hall effect and MEMS capacitive. Gefran has developed a method of using Hall effect in a perpendicular fashion so that it can be used to measure rotation angle. Gefran also uses MEMS capacitive to measure inclination and tilt. These are outside the scope of this discussion, and so I will not go into further detail here. Next, we'll talk about some of the terminology that you will see in specifications for these sensors. Nonlinearity is the measure of how the electrical output varies in proportion to the position displacement measured compared to the ideal straight line. Hysteresis is the difference in electrical output of the transducer between position displacement in increasing increments and position displacement in decreasing increments. Repeatability is the transducer's ability to reproduce identical output readings when the same position displacement is applied repeatedly under the same conditions and in the same direction. Accuracy is the combined error of nonlinearity, hysteresis, and repeatability. It is also known as static accuracy. For the rest of this presentation, we will talk exclusively about magnetostrictive technology and hyperwave. First, we will talk about four physical principles that come into play with these types of sensors: magnetostriction, the Wiedemann effect, the Valari effect, and Faraday's induction law. Discovered in 1842 by James Prescott Joule, magnetostriction is a property of ferromagnetic materials describing their change in size and/or shape when subjected to a magnetic field. A magnetic domain is a region within a magnetic material in which the magnetization is in a uniform direction. This means that, in the domain, the individual magnetic moments of atoms are aligned with one another and point in the same direction. In the pictures below, the area within the red lines is a magnetic domain, and each arrow represents billions of atoms. The non-magnetic material has no clear magnetic domains. In the magnetic material, there are magnetic domains, but they are random and not entirely aligned. In magnetized material, the domains are aligned parallel to each other and produce a strong magnetic field. Magnetostrictive materials are materials where thermal annealing and cold working are used to produce domain ordering and magnetization. In positive Joule magnetostriction, materials enlarge when placed in a magnetic field. In negative Joule magnetostriction, materials shrink when placed in a magnetic field. The Valari effect. Discovered by Italian physicist Emilio Valari, the Valari effect is the reverse of magnetostriction. Whereas magnetostriction is a change in shape of a magnetostrictive material in the presence of a magnetic field, the Valari effect is a change in the magnetic field when a stress is applied to the material. The Wiedemann effect. The Wiedemann effect is named after German physicist Gustav Wiedemann. In a ferromagnetic wire, it describes the torsional force produced at the location of an axial magnetic field when a current flows in a wire. In this picture, if the electric current or magnetic field alternates, the wire will begin torsional oscillation. The Wiedemann effect is the primary principle behind Gefran's magnetostrictive sensor design. This torsional wave force results from the vector addition of the magnetic field surrounding the waveguide due to a current pulse and the magnetic field externally supplied by our magnetic cursor. We will see how Gefran applies this in the coming slides. Faraday's induction law. The electromotive force around a closed path is equal to the negative of the time rate of change of the magnetic flux enclosed by the path. Visually, the magnetic flux through the wire loop is proportional to the number of magnetic flux lines that pass through the loop. In simple terms, Faraday's induction law describes the relationship between the electromotive force measured in volts and changing magnetic fields. It is the key principle behind transformers and electric motors and plays a key role in the operation of our magnetostrictive sensors. Now that we've covered a few of the physical principles that are utilized, let's go over the technology behind our magnetostrictive sensors. A magnetostrictive sensor consists of a transmitter, shown in black with a gold band in the picture, which sends a pulsed signal down a tubular waveguide. This produces a circular magnetic field around the waveguide. The circular magnetic field meets the magnetic field of the cursor magnet and, due to the Wiedemann effect, generates a torsional wave. The torsional wave runs in both directions. On the right side, it goes to the damper and is dampened so that it will not reflect back and interfere with the measurement. On the left side, it is picked up by the coil and transferred to the measurement circuit. The measurement circuit measures the time between the pulse being sent and the torsional wave being received. Displacement is then calculated by time of flight. Here we see an electrical representation of the time measurement. The pulse is emitted, and after the time of flight, the coil receives the torsional wave. Our sensors use a 1 millisecond pulse for sensors with stroke lengths up to 1,000 millimeters, a 2 millisecond pulse for stroke lengths from 1,100 millimeters to 2,000 millimeters, and a 4 millisecond pulse for stroke lengths above 2,000 millimeters. So what is Gefran's new Hyperwave technology? Hyperwave refers to a series of product improvements to the design of magnetostrictive sensors involving the 4 physics principles we discussed previously. The Joule magnetostriction effect is utilized by the metal wire of our waveguide. The cursor causes a Wiedemann effect, which creates the torsional waves that travel along the waveguide. The Valari effect and Faraday's law are utilized by the receiving coil. With Hyperwave, Gefran has not only improved the dampers and waveguide, we have made a drastic improvement to the receiving coil. Prior to Hyperwave, we used a coaxial coil style pickup. This style allowed the detection of torsional and longitudinal pulses. It could detect longitudinal shock inputs and was sensitive to shock and vibration. This resulted in a weak signal and a low signal-to-noise ratio. With Hyperwave, we use a decoupled radial tape style receiving coil. This has several advantages. Due to the decoupling, only torsional pulses are measured. It does not detect longitudinal shock inputs and has improved shock and vibration tolerance. This results in a strong signal and high signal-to-noise ratio. In this slide, you see an electrical representation of the signal-to-noise ratio of the old pickup and the new pickup. It is not just a little bit better, it is 10 to 15 times better. To summarize the improvements brought about by Hyperwave, there is improved shock and vibration tolerance, improved thermal drift properties, greatly improved EMC immunity, and 10 to 15 times the signal-to-noise ratio. The following short video provides a further review of Hyperwave and introduces some of our products that utilize this technology. Now we will take a look at Gefran's full line of magnetostrictive products. The WPG, WPP, and WPA series are profile-shaped analog linear transducers that utilize Gefran Hyperwave. The WPG series is good. It has a max stroke length of 1,500 millimeters, a temperature range of -20 degrees C to +75 degrees C, and a max nonlinearity of 0.04% of full scale. The WPP series is better. It has a max stroke length of 2,500 millimeters, a temperature range of -30 degrees C to +75 degrees C, and a max nonlinearity of 0.02% of full scale. The WPA series is best. It has a max stroke length of 4,000 millimeters, a temperature range of -30 degrees C to +85 degrees C, and a max nonlinearity of 0.01% of full scale. All three of these series are capable of 0 to 10 volt DC, 0 to 5 volt DC, and 4 to 20 milliamp outputs. They can all use either one or two cursors, and they can all measure both position and speed. The available electrical connections include an M12 5-pin, a DIN 6-pin, a DIN 8-pin, an M12 8-pin, and cable out. Available brackets include both a 42.5 millimeter hole spacing and a 50 millimeter hole spacing. Here you see the available magnetic cursors. The PCUR202 cursor is floating and does not touch the sensor body. It must be kept at between 2 and 7 millimeters above the sensor to maintain accuracy. The rest of the cursors slide along grooves in the sensor body and have a threaded axial joint that engages the item to be measured. The WPP-S and WPA-S are profile-shaped transducers that utilize Gefran Hyperwave technology. They have the same specifications as their analog counterparts, except they have SSI output. These are the configuration options for the SSI output. The WRG, WRP, and WRA series are rod-shaped analog linear transducers that utilize Gefran Hyperwave. The WRG series is good. It has a max stroke length of 1,500 millimeters, a temperature range of -20 degrees C to +75 degrees C, and a max nonlinearity of 0.04% of full scale. The WRP series is better. It has a max stroke length of 2,500 millimeters, a temperature range of -30 degrees C to +75 degrees C, and a max nonlinearity of 0.02% of full scale. The WRA series is best. It has a max stroke length of 4,000 millimeters, a temperature range of -30 degrees C to +85 degrees C, and a max nonlinearity of 0.01% of full scale. All three of these series are capable of 0 to 10 volt DC, 4 to 20 milliamp, and 0 to 20 milliamp outputs. The available electrical connectors include an M12 5-pin, a DIN 6-pin, a DIN 8-pin, an M12 8-pin, and cable out. All three of these series are rated IP67 and are suitable for mounting inside of a cylinder. They come with donut-shaped magnetic cursors in 3 different diameters and a floating cursor that can be used to measure liquid level. The WRP-S and WRA-S are rod-shaped transducers that utilize Gefran Hyperwave technology. They have the same specifications as their analog counterparts, except they have SSI output. These are the configuration options for the SSI output. This is the MK4-C contactless linear position transducer with magnetostrictive technology. The absence of electrical contact on the cursor eliminates all wear and guarantees unlimited life. The MK4 can open integrates a microprocessor to process the measurement and to diagnose the transducer. The CAN field bus communication system provides fast and safe transmission. The use of CAN open DS301 protocol and device profile DS406 provides quick and easy integration of the transducer in the control and automation system. It has a stroke length of between 50 and 4,000 millimeters. It is rated IP67. It has either one or two cursors. It measures both position and speed, has a linearity of only 0.02% of full scale, and great repeatability error of only 0.01 millimeters. The MK4-P is an aluminum profile transducer using magnetostrictive technology. The Profibus interface integrates into complex systems with long communication distances, guaranteeing rapid and secure data transmission. Its many advantages include smaller size for easier installation, excellent linearity and repeatability, and high resistance to vibration and shock, guaranteeing exceptional reliability. There are two M12 connectors for simplified connection to Profibus and one M8 connector for separate connection to the power supply. This way, the transducer can be powered without having to be connected to the bus. It has stroke lengths from 50 to 4,000 millimeters. It is IP67 rated. It can handle up to 4 cursors, and it measures both position and speed. The IK4-C is a stainless steel rod-shaped transducer with a threaded flange and can-open digital output. Its mechanical structure offers improved features for in-cylinder use, including a series of new multi-connector models, free rotation of the connector head, and replacement of the internal electronics without removal of the transducer. It has stroke lengths from 50 millimeters to 4,000 millimeters. It is rated IP67. It uses one cursor. It has excellent repeatability of 5 micrometers, and 2 micrometers is available upon request. It operates in pressures up to 350 bar or 5,080 psi. The IK4-P is a stainless steel rod-shaped transducer with a threaded flange and Profibus digital output. It is designed for in-cylinder use. Its many advantages include smaller size for easier installation, excellent linearity and repeatability, and high resistance to vibration and shock, guaranteeing exceptional reliability. There are two M12 connectors for simplified connection to Profibus, and one M8 connector for separate connection to power supply. This way, the transducer can be powered without having to be connected to the bus. Stroke lengths are from 50 to 4,000 millimeters. It is IP67 rated. It can handle up to 4 cursors, and it measures both position and speed. The RK2 and RK4 are rod-shaped transducers that use magnetostrictive technology. The RK2 has a flanged head and is ideal for applications requiring installation completely inside the hydraulic cylinder. It has the option of a start-stop interface, which allows the use of multiple cursors, and an analog interface that gives the displacement of a single cursor. The RK4 has reduced dead zones, and the head's threaded shape is designed for applications requiring the installation of the transducer partially inside the hydraulic cylinder. It is an analog sensor that uses one cursor. Features: they are both designed for inside cylinder use. Their dimensions are among the smallest in the industry, allowing for easy installation. They have stroke lengths from 50 millimeters to 4,000 millimeters. They are rated IP67. They operate in pressures up to 350 bar or 5,080 psi. The RK5 series is a flanged head analog transducer designed for the mobile hydraulic market. It installs completely inside oil pressure cylinders. Its unique design, plus a wide range of cursor configurations, ensures easy installation and total compatibility with cylinder manufacturer specifications. It is highly resistant to shock and vibration and designed for heavy-duty use. It has great linearity, hysteresis, and repeatability. The RK5-C has can-open digital output. Features. These are designed for inside cylinder use. They are heavy-duty for the mobile hydraulic market. The RK5 has both direct and inverse analog outputs. They have stroke lengths from 50 millimeters to 2,500 millimeters. They are rated IP67 or IP69 with connector. They operate in pressures up to 350 bar or 5,080 psi. In conclusion, transducers utilizing magnetostrictive technology come in many form factors, have infinite resolution, come in a wide range of analog and digital outputs, are robust, they are touchless for long life, have multiple cursors, and can measure speed in addition to length. Gefran's Hyperwave technology involves a significant improvement to the damper, waveguide, and receiving coil. This results in 15 times the signal-to-noise ratio, extra resistance to shock and vibration, and strong EMC immunity. I want to thank each and every one of you for giving us your time today. We hope you will consider magnetostrictive technology, and we hope you will consider a Gefran solution. Our sales and engineering team will be glad to assist you with your applications. If you would prefer, you may email your questions to richard.nye@gefran.com. That's richard.nye@gefran.com. We will now begin the question and answer session.